All right, welcome back. We're going to continue with lecture 4A today, where we started talking about psychometric models generally speaking. We had this crazy looking form, you might remember, where my point I was trying to make was your theory about what you're measuring is constant. And that's usually what we call the right-hand side of our psychometric equations, right? That's where our latent variables go. That's where our control variables go. That's how we build that psychometric model. But on the right-hand side, we have this weird looking form, and that's because data come in all different types. And I wanted to get you to thinking about this because just because you may take classes that are separate measurement models, like IRT is a separate class from like factor analysis, both of those have the same theory. We're measuring a construct. The difference between those is that the type of data is very different. And you may think, oh, there's a whole lot of methodology different between the two classes, but a lot of that methodological differences come just from the data being different. So from a big picture perspective, what I'm trying to impress upon you in the latent variable sense is that latent variable measurement models generally have the same theory, but may have different ways of collecting data, and mapping that theory onto the data is largely what we see in our differences when it comes to like something like IRT versus CFA. Are we good with all that? Okay. The other part that we have here is measurement models, generalized linear models. If you took the generalized linear model class, what we tend to do is to model a function of the mean of the data. In a regular linear model, as I mentioned before, if we just had y and we pretended it was continuous, the mean of the data is given by what Lisa Hoffman calls the model for the means, which is just this first part here. In a generalized linear model sense, sometimes this portion of the right-hand side is called the linear predictor as well. So the part that's linear, but because the mean of the data may vary based on the type of data you have, we use this really crazy esoteric notation to denote it, right? So in the middle here, we're saying the mean of y conditional on the latent trait. So this is a conditional mean right here. And if we need to transform that mean onto the real number line, we use a function called the link function, right? So the example I gave last time was if you have a binary item, the mean is a proportion. It goes from 0 to 1, and then we have to apply a link function to that proportion so that instead of mapping our numbers onto the space from 0 to 1, we can still have a linear model that runs the whole number line. What that ends up doing is causing our item characteristic curves to have an upper and lower limit when we do the back mapping, right? This is a link function. Similarly, there's an inverse link function. Once we get to IRT, I'll have a few more examples about that. How are we doing with that idea? All right. And then, of course, there's the crazy case that throws us all off, which is the factor analysis case, where it just says y is equal to, and then there's this right-hand side, and it usually ends with an error term. The mean of y is still given by this model for the mean, everything that's apart from the error. It's just that we don't have to do anything. We're just directly modeling the mean from y. Sometimes we call that a link function, an identity link function, which is basically taking the mean of y and multiplying it by the number 1, which sometimes is called the identity number, right? Cool. All right, let's move forward. Actually, questions? Yeah. I think I left off last time talking about latent variable distributions. We ended with talking about most of the distributions in this class, actually all of the ones in this class, and most of the distributions you see treat the latent variables as some continuous measure. There are a few cases where you may have non-continuous traits. They're very interesting cases. Models behave a little bit differently than them, but they're fun to study from a statistical point of view, but often we don't see them in practice. But let's talk about what we do see when we have more than one latent variable. And in my example here, we said that there were two latent variables underlying this conspiracy theory data, something about tendency to believe in conspiracies about government and tendency to believe in non-government conspiracies, basically, too. So we have to give a distribution to those latent variables, particularly in Bayesian psychometric models. If we think of them as continuous, the most natural distribution we pick is the multivariate normal distribution. Here it is here. In fact, many of you may take a multivariate statistics class. To me, a lot of the statistics that you learn in those classes are somewhat classical, not used a whole lot, but the thing that is not classical, something that is often used is this multivariate normal distribution. This is the PDF, right? Remember the PDF, or the density function. If we were to observe a set of latent variables, if we actually had values for these latent variables, what this PDF tells us is how relatively likely those values are, right? Just like the height of a curve. It's just, instead of having a one value, a univariate number going into a univariate normal, now we have, in our case for this example, 2, or we may have more than 2, right? This vector of values. So what we build as a prior distribution turns out to be this multivariate normal density itself. We have our latent variables that show up here. In this distribution function, it takes the latent variables, subtracts off the mean for each latent variable. In our case, we have to do something to determine the mean. Often that's a 0. Is it mean vector? Means are set to 0 or assumed to be 0 of latent variables often. And then we have a covariance matrix of the latent variables, right? So again, we talked about latent variable identification a little bit last class. We have to do some tricks to estimate the full covariance matrix. More often what we have is something we call standardized latent variables, where this covariance matrix has a diagonal value set of values called of ones. Right? And so if you take a covariance matrix with the diagonal being 1 and you say that it comes from data, then that thing has to be invertible. What I'm meaning is that's a correlation matrix. So correlation is often what we build here if we have standardized factors. But this is our covariance matrix as well. So input into the multivariate normal PDF that we have will be our latent variables, and then 2 matrices or vectors of hyperparameters, a mean vector and a covariance matrix. And unlike what I've showed you in the linear model section, again, each of the mean vector and covariance matrix takes some thought as to how to construct it, because in a latent variable model, you have to choose what the scale is, what we call scale identification. Right? So the mean vector commonly is 0, but we may want to estimate the means, in which case one or more of the items we have to make constraints on the intercept parameters. The covariance matrix, if we want to estimate the variance of each factor, we're going to have to use what we call a marker item, where we make a constraint on the discrimination or slope factor loading parameter for each of the items as well too. So that is our multivariate normal. It is what we are likely to use throughout the class for all of our latent variables. And I will say that the other terms that show up here are all to sort of make this so that this distribution integrates to 1 across each of the dimensions of the latent variables. So what you see here is an inverse covariance matrix. What you see here is the determinant of the covariance matrix. And then, of course, this number is pi right there. You don't have to calculate this. The computer does it, but it is an impressive-looking distribution function. Any questions on multivariate normal? All right. So this is a prior distribution when we apply it to our latent variables right here. Right. So if we choose to put say our variables are continuous, we often pick a normal distribution with it. All right, so let's talk about how we identify the model. Statistical identification. Statistical identification is the concept that basically what you're trying to show is that your model parameters are unique, right? That you have a single set of parameters that may have a maximum in a likelihood sense, or may have a posterior distribution that's not 100% correlated with a different set of parameters as well too. And the first, so we mentioned before scale identification. Actually, that's next. But the first thing we have to think about is, in a latent variable model, we have to have multiple observations from a person to be able to try to estimate a latent variable representing their ability or some other psychological construct. And what we call that is empirical identification. Basically, we have a minimum number of items that has to measure each latent variable. In CFA, the number is 3. Now, 3 with a little asterisk by it. Right? If you have a unidimensional model and you want to estimate a latent variable with no constraints on the model and no constraints on the latent variable, you need 3, right? For one dimension. If you have 2 dimensions, right? If you have a like we have in our example here, then one latent variable can have 3 measuring it. The other latent variable can have 2. And the two latent variables have to be correlated. So to me, the easiest way to say this is to say 3 or more items per latent variable. Now, how many of you have estimated an IRT model on 3 items before? Or a CFA model on 3 items before? I see a lot of shaking heads, thumbs down. Nope. Turns out you can. Like, you don't need my permission. Anybody can go grab R and chat GPT code and do anything they want, right? Or not even R. You can do it in something else. Turns out you statistically can estimate a model with a latent variable model with 3 items. What do you think happens to the latent variable in that case? Do you think you have a lot of information about the latent variable? No. So while yes, you can estimate a model with 3 items, what turns out, let's put it in a Bayesian context, what you would expect to find is your posterior distribution of theta for each person has a very wide posterior standard deviation. Right? That's the Bayesian language for it. Shall I put that in psychometric language that you may have heard before? All right. Your estimates of your conditional standard error of measurement of theta will be quite wide if you're using an IRT model with 3 items. Or if we want to talk CFA language, your reliability for the latent trait will be quite low with 3 items. So yes, people do this frequently, but not in a context where we want to give reliable scores to folks. We teach this class from an educational measurement program. In educational measurement, we do want to provide scores. That is pretty much the first thing we wish to provide to students is a score on a test. We would not design a test with 3 items, most likely, because that score would be very fuzzy, right? We would basically be able to say, that range of theta, if it's standardized, like, -3 to 3, we might be able to cut down half of that with 3 items. We think your theta is somewhere in between this 1.5 standard deviation set. That doesn't do a whole lot of good for an examinee understanding what they may know. However, there are other contexts in psychometrics where this does tend to work. For instance, if we're asking a question about what is the structure of some type of personality instrument, right? How does extroversion relate to neuroticism? Or how does, I don't even know, go on down the list, right? That type of study may not need to provide a score, but much more interesting to the authors in that study are features of the model itself, the model parameters, the structural model parameters, and how we estimate them, and what that tells us about the construct or constructs we're measuring, how they're related. So there are cases where 3 items are used. Generally, not great practice, though. We okay with that? All right. So it turns out this minimum number of 3 is what would be the case in the model data likelihood. If we define the model data likelihood, we can show it's identified for 3 items or more. But remember, in Bayes, we have prior distributions. Turns out we could do some crazy stuff with our priors and take a case where we may have fewer than 3 items per latent variable and make it look like it's identified. So what I'm cautioning you here is, because Bayesian statistics modify, what we're looking for is the posterior distribution, and the posterior distribution depends upon model data likelihood and prior likelihood. It is possible to come up with an identifiable posterior distribution simply by creating very, very informative priors on parts of the model itself. Right? That's a dangerous part of Bayes, particularly in psychometric models, because we don't actually observe the latent variable. So we don't actually know if what we're estimating is really accurate. Right? We have to do extra work to see if it's accurate, if it's valid, if it's reliable, if it makes sense for what we're measuring. So in Bayesian statistics, we can cheat. Yeah, we could cheat. I'll just say that. It's cheating. Anybody think that's cheating? You know, Jonathan, you did an IRT model with 2 items. How did you do it? Magic. And informative priors on my parameters, right? It's not really statistics, it's me, right? And so that's the key thing in remembering about Bayesian statistics, because our prior distributions are subjective. We can create monsters out of our models, potentially, without even meaning to do so. So, as you go through this class, please keep this in mind. I probably will not return to empirical identification again. We will probably have more, well, we will certainly have more than 3 items for every time we do an example. But as you go forward in your own work, remember, use this standard from factor analysis. 3 or more items per dimension to make the model identified. May not make it good in terms of your purposes for your study, but make it identified. Cool? Questions on any of this? I got done drinking and I hear no questions. I'm going to keep going. Let's talk about scale identification then. So empirical identification is having enough data to use your model data likelihood to find to have a shape of your model data likelihood that's unique. Okay? Scale identification is a bit easier. We just need to define what the mean and variance happens to be for each latent variable. And I had sort of mentioned this previously, but I'll mention it again. There are 2 ways to do this, both on the mean side, both on the variance side. For variances, if you want to estimate a variance of a latent variable, you can set one loading or slope parameter to be equal to 1 for 1 item per dimension. That will allow you to identify or come up with a scale variance. If you're in educational measurement, we rarely do that. The reason being, in educational measurement, again, our purpose is to provide scores. And whether scores have a variance of 30 or a variance of 1 is somewhat irrelevant to us. We sort of rescale those scores often anyway, right? So for us, most of the time, if you take educational measurement derived psychometrics, right, an IRT class building on operational IRT, you will come to find out, you may not even know that you could estimate the variance of theta, and I guess in the 1 parameter model you actually can. But the estimate of theta variance is important in cases where you may want to predict theta. I mentioned this the last time, because that variance then needs to shrink. You need to be able to explain variance. For the means, similarly, you can set one item intercept to 0 per dimension, per latent variable, and estimate a mean. Most of the time we don't do this. The only times where I see this used frequently are in measurement and variance methods. So sometimes we have to go and estimate the mean to see if to control for potential mean difference between groups if we have a multiple group model. So if we want to see if items behave the same between multiple groups, we do have to control for the groups potentially having a different mean on the latent variable. So that's part of the steps in measurement and variance, but we could do either. So long story short, because these are latent variables, we have to figure out what their mean and variance happens to be. Sound good? Okay. The other way that we do this is standardized factors, where we set the variance of all latent variables to 1. We set the mean of all variables to 0. And if we have more than one latent variable in the model, we estimate all the correlations in that latent variable correlation matrix. All right, those estimated correlations, you should be very pleased that you're taking this class in 2024, but believe it or not, this last bullet right here was exceedingly difficult in a Bayes sense when I started in Bayes. Right? That's a big difference. It's like what's the difference between my generation and yours? Like life-wise? Well, I can tell you one. I know when I grew up, it was a great treat to ride in the back of an El Camino's pickup truck on the interstate because my dad was driving. And if I did that, I would be going to jail and my kid would be going to foster care. Similar to the lack of seatbelts back when I was growing up, we had a lack of ability to estimate correlation matrix back when I was growing up intellectually. But you're good. We've got this. But it will be, I will warn you, when we get to multidimensional models, it is complex. It is complex. All right, a little bit more on scale identification here. Bayesian priors can let you believe that you can estimate more parameters than non-Bayesian standards suggest. And this is what I was telling you. You can take an unidentified model and get it to work in days. But it's not good when it happens. Oftentimes, you'll find quirks in your data. Your estimates are often unstable. They'll have chains that don't converge, right? You'll see convergence issues all over the place. Or if you do get convergence, it'll be really suspect. It'll have like certain like regimes. It'll be just enough to have an R hat that might be like 1.1, but then when you look at the posterior distribution, like for any variable, it may have different modes, almost like multimodal. So scale identification, or actually, I'll give you another story. In the 1990s, I got into Bayes with this model called the fusion model, which was a fusion between classification and IRT. That was the goal for it. And the fusion model came about because in the 1990s, there was something called the unified model to try to put the two together. And a group of researchers came up with this model, started trying to estimate it in Bayes, started to get numbers out of the computer. Again, remember the 1990s, that was where Bayesian methods, MCMC methods were starting to get to psychometrics. Anyway, long story short, this model is sort of the beginning point of research that ETS, Educational Testing Service, invests in. And then shortly after, contracts and stuff like that, grants come through, they determined, the model's not really identified, right? It was only because we were using Bayesian methods with certain priors that this model didn't work statistically. And so the unified model became the reparameterized unified model, which also was called the fusion model later on, that did allow it to be identified. So the point I'm trying to make is when you're in Bayes, always have it in your mind, always question your results to see whether or not your estimates are working, particularly in the latent variable case, because we don't have the benefit of it. All right, so the most commonly methods that we use, if we are looking for developing a scale or we're looking to provide people for scores, to identify most things, we use the standardized latent variable method. I will show you both methods in class here. Remember, standardized latent variable, that means we set the means to 0, the variances to 1, and we estimate all correlations. If we have cases where latent variables might become outcomes, or we have like a measurement invariance / diff study, where we have to control for certain differences at the group level, when we're looking for differences at the item level, then we switch to the marker item for latent variables as well too. So that's the general guide. The other thing I need to make a point though, when you take Lisa Hoffman's SEM class, right, CFA, the CFA lecture, she talks about this too. Marker items or standardized factors, right? And she talks about how you can transform from one to the other and get one result after the other. And yes, that is absolutely the case in frequentist land. However, in Bayesian land, things are a bit different, right? It is the case that the model data likelihoods are equivalent under a standardized item, a standardized factor, or a marker item case. So our model data likelihood is fine. However, we define a prior likelihood on the parameters of interest within the scale that we set. Meaning, if we pick standardized factor version, our priors might be one version. But if we pick a marker item, our priors might be another. And because of the choice of prior that we're using, the ones I'm going to demonstrate to you, the posterior distributions will not be identical, will not be able to be switched or transformed. Right? So when you pick an identification method, it's true that for model data likelihood, right, the part that we would talk about in the frequentist version of statistics, they are equivalent models under each version of identification. In Bayesian, our posterior distributions are slightly different. They're not widely different, and as n goes to infinity, they will converge to being the same. However, they may be different, and they may not be able to be transformed. So if I decide to use standardized factors, and Vladimir wants to do, marker item, and we look at our results, we can sort of get a translation between the results, but the full shape of the posterior distribution may not be the same if we were to try to compare and contrast. So just a heads up for you on that, okay? It's a little bit weird to think about. All right, any questions about any of this? No questions. I like it. Moving on. So to summarize, for all the psychometric models that we're about to get into, we're going to use multivariate normal distributions for all latent variables. We will also have standardized and marker item identification for the scale. And we will likely form most of our models with today's slope-intercept parameterization. And it turns out, that generated quantities section in Stan that I taught you? We used it for like prediction, and actually we used it for the LOO, the model fit, WAIC. We used it for posterior predictive model checks. Well, it turns out if we form our model in slope-intercept, let's say we're an IRT model and we use a slope-intercept approach, we can always use generated quantities to come up with the parameters of discrimination difficulty as well. So we can easily flip between the two, come up with versions in different ways as well. So next steps, which we're going to be starting right after we get done this lecture today, is we're going to talk about estimating these models with a single latent variable, right? So in the idea of teaching that I'm trying to do, the scaffolding I'm trying to provide you is we started with linear models in Stan, and then we made linear model homework. Next, we're going to start with univariate or unidimensional latent variable models. And I'll show you continuous data, which is CFA, binary data, which is IRT, multiple categories, which is polytomous IRT. And then what we'll do is we will then switch, we'll kind of cover all the details with a univariate or unidimensional IRT or latent variable model as we build the class, mainly to sort of get you familiar with all the different weird things that Bayes has that are slightly different than what you may have learned previously. So we'll talk about each of these different types of models, and each we'll talk about characteristics associated with each type of item. So each distribution we use actually brings about a few different nuances to the model. And then finally, once we've done all that, that all stays the same, and we switch to multidimensional latent variables. And that latter switch, if I were to do that first, I think it would probably, there's too many moving parts. So my thought is, let's leave the latent variable simple and make it complicated on the items, get you familiar with how that works, and then once you're familiar with it, we'll go and make the latent variables complicated too. Okay? All right. For those of you who are like me in grad school, who really resented anything that unidimensional because it was boring, that was what I used to call it. It's boring. I apologize, it'll be boring, but I'll spice it up, I promise. There'll be some weird results that I want to show you, and I'm going to show those to you in the next video. I think that's like a tease, right? I'm going to tease the next video. I don't know, for those of you who aren't here. Vladimir, question? Yeah. Correct. Yes. Yes. Yeah, apologize for that. Yes, the numbers themselves. So if you use a standardized factor versus a marker item in a frequentist non-Bayesian model, like you go into Levon or you go into M+, and you try the two different estimation methods, what you will have is, yes, different numbers. Like the numbers, the factor loadings are different because the variance of the latent variable has changed. In one case, it's the value of 1. In another case, it might be bigger than 1, right? And so those numbers are very different. However, in the frequentist sense, you can use a transformation from one to get to the other and get the same results as if you had run both models the same. So basically, you can run a standardized, or pardon me, you can run a marker item model, and then with a few commands, you get the standardized factor results because it's a sort of a linear transformation. And the results are invariant to linear transformation. However, and actually in the frequentist approach, you get the same point estimates, and there will be a transformation needed for the standard errors, but that's done behind the scenes, right? But you will be able to basically derive one from the other. In Bayesian, that's not as straightforward because if you think about it, if you put prior distributions, let's take the case where you have a standard normal prior, like a normal distribution mean of 0, standard deviation of 1 for, let's say, a factor loading. In the case where the model data likelihood says it's a standardized factor, that applies to a number that's likely to be smaller than in the case where you have a number, have a identification where it's a marker item, right? And because of that, the posterior distributions will be different. But not only will they be different, they will not be able to be transformed one-to-one onto each other. And that's the key difference. In the frequent, if all we had was the model data likelihood, we could get a one-to-one transformation from one identification method to the other. Because we have this posterior distribution that is formed by priors that are not equivalent under transformation, then the posterior distributions will not be equivalent under transformations either. That may seem a little bit startling to you, but most frequently it's sort of not a big deal because often when we identify a latent variable, either standardized or marker version, we use the context of identification to describe the result. And that result will still be the same. It's just the one-to-one mapping is not the same. I hope that helps answer the question a little bit. Excellent. Excellent, excellent. Any other questions? Like it. No questions. I have to make the question noise. I'm noticing I'm doing that too. I hope I've stopped hitting my desk. I don't know that I have, though. But the question noises, all these weird old man noises coming out of my mouth. All right. Stop the recording.